In the last lesson, we learned about energy, kinetic and potential. And if you think back to the potential energy, let's look at the bow and arrow. When you pull the bow back, you have the arrow in there ready to be fired, and you release the bow. The bow then puts a force on the arrow and propels the arrow forward. What we say that is we say that the bow did work on the arrow. The bow applied a force over a distance, doing work. The bow itself, when pulled back, has potential energy, stored energy. This energy allows it to do work. One of the ways we define energy, as we say, energy is the ability to do work. So in kinetic energy, if you think about a moving object, like a hammer, if you have a nail and you're getting ready to put it in the board, it takes work to drive the nail in the board. So the kinetic energy of the hammer gets transferred into the nail, driving into the board. The kinetic energy allowed us to do work. Again, energy, it gives us the ability to do work. So whether it's gravity doing the work or the hammer being swung that does the work, something has to have a force that allows it to do the work. In the first scenario, gravity is the force. In the second scenario, your hand is the force. So to do work, you have to have a force, and it has to be applied over a distance. So the child in the swing has a certain height relative to the ground. That's the distance that the force of gravity is acting upon the girl, allowing her to gain velocity or doing work. The unit of work is joules, just like energy, because they're essentially the same thing. Here we can see this relationship. As we pull back the bow, we're doing work on the bow. We give the bow potential energy. When we release the bow, now the bow is doing that same amount of work on the arrow. The arrow then gets kinetic energy. So the work we put in is put back into the arrow. The more work you put in, the faster the arrow flies. Same thing with the person on the swing. The higher you are, the more potential you have, the more potential gravity has to do work on your body. As you swing downward, that potential energy is changed into kinetic energy. Gravity has done work to increase your speed. In your car, obviously the gas pedal gives energy to the engine. Through the gas it gives it and allows your car to speed up. Work is equal to the change in kinetic energy. One thing about work is if you don't move an object, you're not doing any work. So you can apply a force and not do any work. Let's say you're pushing on a wall, or back in middle school in gym class, you'd have to do wall sits. Remember doing wall sits? And you'd sit against the wall and the gym teacher would be like, if you were goofing around, make you sit there for 30 seconds and your legs would be burning. Well, you weren't doing any work on the wall. You weren't moving the wall, so no work was being done. If you don't move something, if there's no distance that the object moves over, no work is being done. You can see the man in the black shirt carrying his books. The force that he applies to the books is upward. He is moving horizontally. He is doing no work on the book. The book has to move in the same direction as the force for work to be done. Like if you're doing a curl in the gym. So you got your 40-pound dumbbell and you're just walking around the gym talking to people. Are you doing any work to build up your biceps? No. The only way that you do work to build up your biceps is if you curl that dumbbell, if you lift it against gravity, so that the direction of motion of the dumbbell and the force are in the same direction. This man mowing the grass, as he applies a force down the handle of the mower, only the horizontal component of the force is doing work. Only the force that's in the same direction as the distance is doing the work. The force that he pushes down on the mower isn't doing any work. The mower's not going into the ground. So the steeper the angle, the harder it is to mow the grass because you have a smaller horizontal component to the force. Simple machines allow us to make the work easier. They do not decrease the amount of work. They just make it easier. So when we look at a simple machine, we say the work we input is going to be equal to the work we output. So the amount that we put in is what we're going to get out. Now what changes is the force. It seems like it's easier because you're applying less force. But as you apply less force, it goes over a greater distance. So as we look at the next 6 simple machines, we're going to see how the forces change with the distance. The first simple machine is an inclined plane. An inclined plane allows you to lift at an angle, so your force is over a greater distance. The pallet or the boxes being moved up the ramp are a lot easier to push up a ramp or carry up a ramp than to lift vertically into the back of the truck. Same thing with a ladder. As you go up a ladder, it's easier to go up a ladder at an angle than it is to go up a very steep ladder. This is why wheelchair ramps are at a very shallow angle. A very steep wheelchair ramp would be very difficult for the person in the wheelchair because they'd have to apply a great force. What they do is they make them very steep, and they even curl around or double back so that you have a much bigger distance that you have to move horizontally so you can apply less force. The next simple machine is a screw, and a screw is just an inclined plane wrapped around the cylinder, and we have a wood screw, an auger, a corkscrew, and then at the bottom we have an Archimedes screw, and you can see how the Archimedes screw moves the little balls up the inclined plane. Archimedes screws are used a lot for water, so you can have a water move upwards using an Archimedes screw. You kind of like when you're using an auger in your backyard to drill fence posts, holes. You know the dirt comes up out of the hole when you're using the auger. Same principle here, or a drill bit. It's pulling it up. So a screw makes it easier. If you have a machine screw, it's a smaller pitch between the threads. It takes a lot more turns than a drywall screw where there's a greater pitch between the threads. But you don't have to apply as much force when you're turning it because the more turns it has, the less force you have to apply. Remember, force and distance are going to equal the amount of work you have to do. So if you want to decrease the force, you increase the distance. Levers are simple machines. Levers are characterized by a fulcrum, which is your pivot point. The further away your effort is from the fulcrum, the easier it is to pivot. So the longer your lever arm, the less force you have to apply. And there's three classes of levers. There is a first class lever with the fulcrum in the middle between the load and the effort. A second class lever where the fulcrum is at the end and the load is in the middle. And a third class lever where the effort's in the middle and the load's at the end. And I have three examples at the bottom. A pliers would be a first class lever. There's a lot of first class levers. Seesaw is a very common one. A second class lever. Here we have a nail remover as a second class lever. You can use a lot of these as well. A wheelbarrow is a good example of a second class lever. And then a third class lever, we have some chopsticks. Chopsticks are a great example of a third class lever. A shovel can be used as a third class lever. If you have the dirt on the head of the shovel and you're holding the end of the shovel as a pivot or a fulcrum, and then your hand is in the middle to toss the dirt, that would be a third class lever as well. A wheel and axle. For a wheel and axle, it's just not any wheel that spins like on a Matchbox car. A wheel and axle is going to have crank on it, so that the longer the crank, the more mechanical advantage you get out of it. So it's easier to crank a bike with long pedals than with short ones. A steering wheel as well, a really small steering wheel, you have to turn it a lot of times. If you ever had a stubborn faucet, you know the longer that handle is on the faucet, the easier it is to turn it. And then a Ferris wheel would be a good example of a wheel and axle. A pulley is an example of a simple machine. The more pulley cords you have, the higher your mechanical advantage is because you're going to be going around more turns. You're going to be carrying it up a greater distance. The less pulley turns, the less mechanical advantage you have. So what you do is you count the strings. So if you have 10 strings, that would say your mechanical advantage is 10. So your force is going to be 10 times less. So you have to lift 100 pounds. You only have to apply 10 pounds of force. And our final simple machine is a wedge, which is just a movable inclined plane. So a wedge has the same idea as an inclined plane, except now you can move it and put it where you want it. And it, again, makes things a lot easier. So those are the simple machines. Another aspect here that we want to talk about in this lesson is power. And power is the rate that you do the work. The rate or how fast work is done. That's going to give you power. If you have a Ford Shelby and you want to have an 850 horsepower engine in it, that's a very powerful engine. You're going to be able to move that car very quickly. You're going to be able to move it very fast. If you only have a 200 horsepower engine, right, you're going to do the same amount of work. It's just going to take you longer to get from point A to point B. and this is going to be less horsepower. Work per unit time, the unit in the SI is a watt. Joules per second is a watt. So a lot of times we talk about light bulbs in terms of watts. A 120 watt bulb is going to be a lot brighter than a 60 watt bulb. It's doing more energy in the same amount of time. And finally, in this lesson, we want to talk about energy conservation. And energy conservation, we mentioned it last lesson when we talked about energy transferring forms from one to another. Well, when energy is transferred from one form to another, it doesn't get lost. The energy is conserved. The total amount of energy is the same. Now, you may lose some to friction, which is thermal energy, so that would be like a third energy. But here in our roller coaster example, you can see as the roller coaster goes up to the top of the hill, the potential energy is at its max. Then when it goes down the hill, the kinetic energy at the bottom is at its max. And at all points in between, the potential is transferred to kinetic, and then the kinetic is transferred back into potential. It's a give and take. Likewise with the balloon, the potential energy is stored in there when it's blown up, and then when you release the air, that potential energy is transferred into kinetic energy. The energy is conserved, is transferred from one form to another. If we're talking about photosynthesis, the energy from the sun is transferred into the chemical energy in the plant, and it allows it to grow and turn green and do everything it does. Energy cannot be created or destroyed. All the energy we have on the earth right now, or in our universe right now, has been here and will always be here. That's the conservation of energy.